going to test see if our recorder works today. Some days it does, some days it doesn't. So as I mentioned, this is one of my favorite sections. I think it's kind of cool. It brings together a bunch of the ideas that we've already talked about and puts them into kind of a new arena. Implicit differentiation. How's our vocabulary, English vocabulary? What's explicit versus implicit? We know the vocabulary meaning?
It was
yes.
Like last year.
One of them is like, is one of them implied, and then the other one is stated outright?
Stated outright. You talk about sometimes pictures can be very explicit pictures, and it's like, okay, we leave nothing to guess, right? It's right there. And the other one is implied, where I don't know what it is exactly. That's essentially what's going on here. So, top equation here. What is that? Circle, there it is. And if I wanted to, I could solve this equation for y. And so I would subtract x squared and then take the square root, and of course you have to do the plus or minus. So if you wanted to graph this equation, because of course the circle is not a function, if you wanted to graph that equation, you'd have to graph both of them on your calculator separately. The plus one would give you the top half of the circle, the bottom one's going to give you the bottom half of the circle. By the way, that is a topic that will come up later on this year. They will talk about, we're going to do some things where you have to be able to figure out what the equation of the top half of a circle is. It's just take your normal circle, just solve for the equation, top half. Sometimes it's bottom half. Okay, but sometimes when we have nasty equations, and that's not particularly nasty, we can solve for y. That's what this is saying. But sometimes you can't. You can fiddle with that all you want. At least as far as I know, you're not going to be able to solve for y. There may be some way of doing that that I'm unaware of. But for our level right now, we can't solve this equation for y. And so then all of those things about finding tangent lines and derivatives, because everything we've done has been dy dx, the derivative of y with respect to x. And that means the y, it's an equation that says y equals. Well, so here's what we're going to do. We're going to find the slope of a tangent line at the point 3, 4. Well, first of all, let's make sure 3, 4 is on the graph. 3 squared is, when I plug it in, 3 squared is, what is 3 squared? 9, and 4 squared is 16, and 9 plus 4, or 9 plus 16 is 25. Yay. So let's pretend we can't solve for y. We just did a minute ago, but let's pretend we can't. So in this equation, I know that y is a function, all right? A moment ago we solved for it, so, but pretend like we don't know what that y is. But does it make sense that when you see y is not a variable anymore, y is a function. Y equals square root of blah, 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 right? Y is a function. So when I want to do, let me back up for a second, when I want to find slope, which is dy over dx, x is a variable, and y is a function. So when I see this equation, I have to think about x being a variable, just like normal, but I have to think about y being a function that I just can't solve for. Yes, okay, but we're pretending we can't solve for, like in that other equation where there was one where we couldn't. So we're going to pretend we can't solve for y, and so y is some function, I just don't know what it is. So what I want to do is take a derivative, right? That's how we find slope of a tangent line. So I'm going to take the derivative of this side, I'm going to take the derivative of that side. Kind of like, simple algebra. If you do something to one side, you got to do it to the other side. I'm going to say this a bunch of times. Y is a function, not a variable. X in this problem is a variable. So now when it comes to taking a derivative of a product, nope, let me try that again. When it comes to taking a derivative of a sum, we just take the derivatives of each individual term as we go through. Oh yeah, I forgot. Think of y as a function, not a variable. You're going to have me say that a few times. So I'm going to take the derivative of each of the individual terms in this equation. Now we'll start with the easy one. What's the derivative of That's what this sentence is saying. What's the derivative of x squared? 2x. Nothing magical there. The derivative of x squared is just going to be 2x. Stick that out front. But here's where things get more interesting. Since y is a function, you have to look at that as a composite function. The outer function being x squared, and the inner function being whatever y is. Some other function, right? So you got to look at this as a composite function. So how do we take the derivative of a composite function? Well, derivative of the outside, the 2 came down front. The exponent got smaller by 1. So derivative of the outside evaluated at the inside times the derivative of the inside. Now that's doing that using the Leibniz notation, that dy dx. Let me finish out. And so then, of course, the derivative of a constant is just 0.
So you can't just say the derivative of y is 1 because it's not a variable.
Right, it's a function. And whatever that function is, its derivative, okay, we're pretending we don't know what it is, but remember it was a square root?
Yeah.
With 25 minus x squared in there, and the derivative of that square root with the 25 minus x squared was not 0.
Yeah.
Or not 1. Or it was something, but I don't know what it was.
What's the point of how many phrases? Is y gonna stay like that, or are we gonna eventually
Y is going to stay like that.
stay?
It's going to stay dy dx.
But then we're treating it as a variable and not as a function if we're never gonna like change it back.
No, it's a function. When I do dy dx, y is a function. But it's the slope of the function. Hang with me here a second. You'll see. I'm not quite finished yet. So what I'm going to do is I'm going to solve this equation for dy dx. Remember what the original question was? The original question was find the slope. The slope is dy dx, right? So if I can solve this equation, for dy dx, what I have over there will be the slope.
Is dy?
Or think of it as y prime if you want. These mean the same thing.
Oh, so it's the same thing as like what you have written over there, just the y's like pulled out along.
Right. This means the derivative with respect to x of the function y.
Okay, so if y was like, it was just like r or something. It's just
It would be dr dx.
Okay.
Right. So, well, let me back up here. So look what I'm going to do. I'm trying to solve for dy dx. And so I'm going to simply divide both sides by 2y. Now, the key to this problem was they told me where they wanted to find the derivative. But not only did they tell me the x value, they told me the y value. And look what this is saying. The slope of this function y, that one we're pretending we can't solve for, the slope of that function is not just in terms of x's. It's not just in terms of x's over here. It's in terms of x's and y's. But I know both an x and a y value. After I simplify, I get negative x over y, and then plug in the values. Plug in the values. I think I went too far. Nope, I didn't. Okay, so then plug in the values. So I know x was 3, I know y was 4, so the slope is negative 3/4. Now, just for the sake of argument, take out your calculator and graph that top half of that circle, which was the positive square root of 25 minus x squared. Graph this equation down here at the bottom and see if it looks tangent. This.
So at the end part, when we're plugging the x and y values in,
You're finding the slope of the tangent at that point.
So we're plugging the point in, so then y isn't. Oh, but it's like, it is a function, it's just like the result of the function almost?
Yes, because we're told what the result of the function is. That's a good way of thinking about it. We're told what the result of plugging 3 into this equation is, even though I have no idea. So y is 4 when the x value is 3. I like the way you said that. That's a good way of saying it. It's the result of the function. I used to always say it's kind of like, it kind of means both things. It's the actual y value, and it's a function.
Okay.
But they told us the result of the function. I like that. Does it look tangent-y?
Yeah, and like match up that's the ground. Table.
Well, give me your. Oh well, I want the equation. I want this equation. I want to see the tangent line.
Oh, the line.
That's supposed to be the equation. That's supposed to be the equation of the tangent line. And and you got bottom and top. Looks good. Yeah. Now you guys do remember why they're not looking in circle like because of your scale. Yeah. Okay. We good? So. Oh, it didn't stop. Oh well. We're still recording. Let me get this out of the way. So there's a big gap in there. Sorry. All right. So same problem, different notation. This is what is more easily done. It's easier to do it this way. I'm going to do the same question. Here's a function, or here's an equation. Find the slope of the tangent line at the point 3, 4. And so x is a variable. Because I'm doing slope, slope is dy dx. dy dx. And so that's what tells you what the variable is and what's not the variable. dy dx, x is the variable. Later on, we're going to do some stuff where it might be dy dt, and time is the variable. In that case, both x and y have to be treated as functions. But right now, just the y is being treated as a function. So, but this is the same thing, right? Y prime was what we wrote before as being dy dx, or d dx of y. And so you get to the same place. It's just the notation's easier to work with here. All right, so let's go back to that other one I gave you as one we couldn't solve for, and walk our way through the process. Same question. Find the equation of the line tangent to this curve at the point 3, 3. Just for the sake of argument, let's verify 3, 3 works. 27 plus 27 is 54, equals 6 times 9 is 54. Good. So the point 33 is on that curve somewhere. So I should be able to find a tangent line to it. So step 1, I am doing I'm looking for dy dx. So x is my variable. That makes y a function. The trick is you got to recognize that guy as a composite function. So x cubed, derivative is just plain old 3x squared. Then you got to shift gears in your brain when you get to the y and do it as a composite function. Derivative of the outside, 3 comes down, 2 gets smaller, or the 3 got smaller to 2. Let me start over. Derivative of the outside evaluated at the inside times the derivative of the inside. Equals, and here's where it gets kind of fun too. This is a product. So the derivative of the first, I let 6x be the first. The derivative of the first, derivative of 6x, 6, times the second. The second is y. Plus the first, 6x, times the derivative of the second. Now the goal is to find dy dx. dy dx is y prime, which means I got to solve this equation for y prime. Algebra 1 at this point. Well, maybe algebra 2. But you're getting everything together over onto one side. All the x prime or y primes came to the left, and all the non-y primes I took to the right. What do I do? Factor out a y prime. And then divide. So notice that the derivative of the function is dependent upon the x and the y value. And then well, yeah. And then come to the fact that I want to use the point 3, 3 and do a little chug and plug. Plug 3, 3 into that thing. So 2 times 3, 3 squared, 3 squared, 2 times 3. I end up with -1. Maybe yeah.
No, just kidding.
Okay. Finally, I got the slope of the tangent line. Now, of course, you plug it into the your point slope formula. It was y minus the y value equals the slope, x minus the x value, which was 3. So y minus 3 equals negative x plus 3, y equals negative x plus 6. That, by the way, is what that curve looked like. The reason, of course, you can't solve it for y very nicely is it's not a function. And when I do the tangent, that's what it looks like. I've got some graphing software that'll let me graph non-functions. That essentially is how every single one of these works. Now, what they're going to layer onto there, like you saw in this last one, we're going to have product rules, we're going to have chain rules. You've got to keep kind of in your head what's the function, what's the variable. And so you have to kind of switch gears back and forth midway through a problem between how do I do just a plain old derivative and how do I do the derivative of a function using chain rule and things.
Just when we plug in, like start plugging in, should we set that equal to? Would we just say it's equal to n, or should we do y prime?
Y prime. It's y prime. You could go like this if you wanted to. Y prime of 3 comma 3.
Okay.
It's m. The slope of the tangent line at 2. It's both. Yes, sir.
As we're working through that equation, should we always simplify if possible? So, like, if we say product rule,
You mean?
what should we always break it up? I'm not, like further up, like you broke up the product rule.
Yeah.
X, y. Should we automatically just like break this up and see it?
Yes. Now you could have something where. Yes, I'll leave it at that. If I understand your question right, I think so. So, kind of cool. I don't know. I think it's pretty slick. That's it. That's the concept. We have. Get this up. Get this turned off. Goodbye. See you.